Today we'll be training a neural network on the MNIST dataset again, except this time we'll be training it the usual way. Last time we did it only using tensors, but today we'll finally be using the PyTorch modules, which will make it a lot easier. So yeah, let's just get straight into it. So I've imported a few libraries. I've imported Torch, obviously, and then we've imported torch.nn as nn. That's just for convenience. So it's going to allow us to use the modules. Then we've got Optim as well. We're importing that, and that's going to allow us to bring in the optimizers. And finally, we have Torch Vision and the other submodules, which is the transforms. So that's going to allow us to transform from like a pillow image, if you remember from the last time, into a tensor. And then finally, we're going to have a data loader as well, which I'll explain in a bit. So let's just run this, and let's create a new block salon. Right, cool. So let's just make a transform quick. So we're just going to grab the two tensor transform. So as I said before, this is the data that we're going to get is an image, and we want to convert that to a tensor. So that's why we're doing that at the moment, and that is transforms. After that, we're actually going to load the dataset. So let's just load the trained dataset, and we're going to have two different datasets of the same MNIST images, except one's going to be used to validate our model, which I'll explain later, and the one's going to be used as the training data. So let's just go data, then we're going to go train equals true. So that's the training. Then we're going to transform. Transform equals transform. Lastly, we'll just have download equals true as well. Okay, let's just copy paste this. Actually, wait. After that, we're gonna make a train data loader. So train loader, we're just gonna call it that, and then it's gonna equal to data loader. We're gonna pass in our data set we just defined, and then we're gonna have our batch size equals to 64. And lastly, we're gonna have shuffle is equal to true. What is this? Oh, it's supposed to be a capital R. Alright, so what the train loader does is that it takes the images and it batches them into groups. So in this case, the batch size is 64, so it's going to take 64 images and batch them together. And it's just going to randomly select them because we use shuffle. If it wasn't shuffle, then we'll just take the first 64 and then the next 64 and so on until it reaches the end of the data set. And yeah, that's we'll just have to do that for the test set now as well. So let's just change this quickly and just copy it. This is going to change the test. This also change the test. Change this. Don't think this needs to be shuffled because this is for validation. Once that is done, we're just going to hit false on that because we're not training on it, we're validating on it. So we're just going to hit run. So next we're actually going to define the neural network. So we do this by making a class that extends from the nn.module. So let's just do that. So we're just going to name this, just name it nn. So we're going to go nn.module. And so yeah, that's extending it. And then we're going to have to make an init function. And then first of all, we're going to have to call the super of this. So this class over here. So we do that super and then comma self, a comma, then we do init. So we're calling this init of this module over here. It's not the MLP, it's nn. So once we have that, we're first gonna do our first layer, which is a fully connected layer. In PyTorch, it's known as, I forgot a self over here. That's why we're getting these squiggly lines underneath here. But yeah, so nn, so the fully connected layers, the nn fully connected in PyTorch is the linear layer, which basically it's just the matrix multiplication of our last tutorial. So we have this. It's just going to make what this class does. So in this line, we're making an object of the class nn.linear, and what nn.linear does is it makes that W1 or W matrix. This matrix is going to be a two-dimensional well, tensor actually. It can be a matrix as well, and it's going to be 28 times 28, so 28 squared by 128. And if you remember from the last tutorial, that is the roundabout the dimensions of our previous weights as well. So when this module gets called, it's gonna matrix multiply the matrix, the W matrix in here with the inputs, but we'll get into that now. So of that, we're gonna actually just make the relu, which is just nn.relu, and we'll also do two more fully connected layers. So equals nn.linear, and then this has to be, the first input of it has to be the 128, which would be 128, and then 64. Of that we'll have self.fc3, and then we'll have nn.linear, and then we have to take the neurons from the last layer, which is 64, and then this is going to be our last layer, so this has to equal to the number of classes, which is 10. Cool. So next we're going to do the forward function. This is pretty simple. Forward. So yeah, when this nn gets called, say like you have an image input equals some tensor, then we just call the network by doing this. So the output is equal to nn dot and then some tensor. And that's how you'd call it, but we'll do that in a bit. Alright, cool. So next we're going to, so we first have to flatten the image that gets passed in. Self, x, and then so x dot view, and x dot size. X would be the input. So this is taking the batch dimension, which is 64 in this case. And then afterwards, this is just flattening it by saying, okay, just flatten the rest of the dimensions. So next we'll have x equal to, so the first layer, which is the fully connected. So we'll have that. Let's just space this out. Then we're passing x in here. Then we'll do x again, self.relu. So activation function for this first layer is going to be relu. And then we'll actually make do the same thing. So fc.to x equals self.relu again as activation. And lastly, x equal to self.fc3 of x. Then that's the output of the network layer, and then we're just gonna return x. Then yeah, that's, now we're just gonna make our model equal to this nn. I think this should be fine. Oh, we got an error. Oh, forgot the double underscore. Should be fine now. Cool. Alright. Next, we'll make the criterion, which is basically just the loss function. If you remember, we used the negative log likelihood, which is just the cross entropy loss. If we're doing binary classification, we'd use binary cross entropy, but we're going to use just cross entropy for now. And so this is the loss function. Then we're going to make the optimizer. This is going to equal to optim.atom. Actually, we'll just do SGD. Cool. And then we'll set the, so we first have to pass in the parameters of the network. Then we're going to set the learning rate as well, equal to 1e to negative 3, so that's 0.001. So basically what we're doing here is this optimizer function is going to optimize the loss, so it's going to try and make the predictions as close as possible to the ground truth labels. And we're saying, okay, you gotta optimizer, we're passing in the model's parameters, which is these the parameters inside the linear layer. So this would be the weight matrix and also like the biases. So, and we're telling the optimizer, okay, keep track of these metrics, and then you can change them to kind of optimize and lower the loss, which is the cross entropy loss. Okay, so let's run that. Alright, so next we're going to make the training loop, which is just for. So let's first do it just for one epoch, which is just one iteration of the dataset. So we're gonna have 1 over inputs, comma labels. So just doing this because I want to put in numeric here. Train loader. Let's just print out the input.size to show you guys what we'll get here. And then we print out also, let's print out the label. Yeah, the labels. Cool. And then let's just break off that so we don't actually keep iterating. So you can see we're gonna get a 64 images, and this is the image. It's a 28 by 28 image, and it's grayscale. That's why there's one there. So after that, it's gonna be flattened. So this would just become, these 3 dimensions would become 1 dimension. This is what this line is doing. And then you can see the labels as well over here. But yeah, you can see that the labels will be the 64 as well. If you just, yeah, cool. Alright, so now we have that out of the way. Let's just actually start coding our training loop, which should be, so outputs equals model, and then we're getting the inputs, which is the images. Once that is done, we're going to do, that's not, let me just change that to input. So once I have that, we're going to calculate the loss. You can see it's a lot quicker to do the forward pass now. So it's 2 lines, as previously it was more than 2. It was like quite a few actually. So next we have we're going to do the backward pass already, so this would be the backward pass. It's just the forward pass. Cool. So next we have the backward pass would just be optimizer dot 0 grad, then loss dot backward. So yeah, we're just in this optimizer here, we're setting it to 0 grad, so it's not setting all the gradients to 0 again. Because there might be some gradients lingering from like previous iterations, so just setting to 0. And once that's done, we're gonna compute all the gradients again, and then we're gonna tell the optimizer to step in the direction of optimization, so it's gonna decrease the loss here, which is, yeah, our goal is to make the loss as small as possible. So the running loss would be equal to loss.item. Let me just actually, so yeah, let's just print the running, so print loss.item. Let's see what happens here. Actually, we're gonna do this for every I plus 100. So every 100, just put bracketing over here just in case. You can take this out actually. So we're gonna print the loss after every 100 batches. So let's just run that. can see that it's beginning to lower a bit. Cool. So let's just let's continue. Let's actually make this, let's log this a bit better. So this is for one epoch, so this is for one iteration of the dataset. But let's actually make it iterate over, let's say, 10 times. 10 isn't really a random number, it's actually just more of like a rule of thumb that we normally use in classification. Classification problems. So running loss is equal to, then correct equal to 0.0, then total examples. So we're gonna track the loss for over 100 steps, and then we're gonna reset it. We're also gonna do this for the number of correct, and then we'll do it for, we'll also have like total examples so we can check how many are actually correct, because I don't think it's always gonna be, you know, 100 times 64, which is like 6,400 examples. So let's just code that. So let's just first do the running correct. So running loss, which is equal to plus equals the loss.item that we have below, and then we'll have, so running correct. This is a bit so what we're going to do is we're going to have torch.argmax. Actually just show you guys quick before I do this break. I'm just going to break this, so we're printing torch.argmax. So this gets the maximum of the outputs at the first dimension. So we're doing it instead of like, so we're going to have like a two-dimensional vector, like let's say 1, 1, 2, 3, 4, then we're going to have like 5, 9, 2, 10. So we're going to have a two-dimensional, and when we say argmax of dim1, the first dimension, which is the 0th dimension, would be the along or vertical, and then this the dimension 1 would be, or the second dimension would be horizontal, because tensors are indexed at 0 and dimensions are indexed at 0, so that's why we're doing that. So if you print that, you can see we're going to get 64 numbers. You guys can just trust me on that. Yeah, and the reason why it's printing so many times is because we're looping through it 10 times. So yeah, and then we're just gonna check if this is equal to the labels. So labels also have a 60, we printed earlier, but it's a tensor of 64. Then what we're gonna do is we're gonna get booleans, but we can actually just sum them. So a true value is equal to 1, and then false is equal to 0. So we're just gonna sum all the values there, and that will give us the number of correct. And so we can just append that to running correct, so plus equals, and then just have to take away this bracket, and then we're just gonna get the total size as well, total examples plus equals, and then we're just gonna get the batch size, or the first dimension, or the 0th dimension, if you wanna. So cool. Okay. Lastly, we're actually gonna change this print statements a bit. So I'm actually just gonna do a f string, so epoch equal, so epoch, and then it's gonna be the epoch above here. We have an f string, yep. And then afterwards you're gonna have batch, and then this is gonna, batch is gonna be I plus 1, then loss would be the running loss, and then this would be divided by total example, so we get the average of the losses, and then we're gonna set that to, like, let's say 4 decimal places. Let's just do another f string over here, and we can do accuracy, so it would be accuracy, then we'll take the running correct and divide it by the total examples, and then we can put a percentage here. Let's just times this by 100 to get it to a percentage. Cool. I think we're ready to train this. Let's see what happens. So as you can see, it's it's training, and it's the accuracy is increasing while the loss is decreasing. So yeah, it seems to be finished training, and you can see that we actually end up with almost 80% accuracy, which is pretty good. We can probably optimize this by using like a better optimizer. I think we can get closer to 100% if you use the Atom optimizer, but we won't use that for now. So there is a bug in our code actually. I think there's a bug when we're logging the accuracy. So first of all, yeah, we don't have a space there, so let's just put that in quick. And secondly, we actually didn't reset the running and loss and the running correct, so let's just do that quick. And cool, let's run this and see what we get now. So the bug wouldn't actually affect it that much because this is resetting after every batch, well, every 100 batches, but in this case it would be resetting after every epoch, which is completely fine. Then the last batch of year would be basically like the percentage correct after every epoch. But yeah, we can just stop this and we can move on to actually the validation, which is also very important. Alright, cool. So now we're going to go into model evaluation. So model.eval, but actually we forgot something in the training loop, which is we have to set this to we have to set the model to, so model.train. So this will tell a PyTorch that we have to track the gradients, but if you go model.eval, it won't track the gradients. So we're gonna be tracking the number correct and the total number. So let's just go with torch dot no grad. It's also telling PyTorch that we're not going to be tracking the gradient. So we're just gonna do inputs, comma labels, in test loader. And this would be outputs equals model, and then inputs. Finally, we'll do, so predicted would be equal to arg torch.argmax, which is what we did previously, and then we're gonna have the outputs again, and we're gonna afterwards we're gonna do dim equals 1, and then the total will be plus equals labels dot size of 0, and I put correct. Then lastly, correct plus equals predicted. So labels, and then we're gonna dot sum this, and let's just dot item it as well, so we don't get a tensor afterwards. Cool. And then finally, you can just run this while we do another line, which is we're gonna say accuracy is equal to 100 times the number of correct, and then divided by the total, then print f.test accuracy. And then we're gonna have the accuracy, and we're just gonna print the accuracy. Let's say to 2 decimal places, put a percentage at the end there, and then we just run this. and we get an 87%, which is similar to what we were getting with our batches. But yep, thank you guys so much for watching. I hope this was very useful to you guys. That's how you train a neural network the correct way using PyTorch. Please leave a like and subscribe, and see you guys in my next video.